Hello everyone, this is the ninth lecture of the lecture series on open channel flows. In this lecture, we will continue our discussion on uniform flow in open channels. Now in the last couple of lectures, we have been discussing on uniform flow in open channels, and in the last lecture we introduced the concept of normal depth of uniform flow, and we also discussed the concept in detail. uh, we know that normal depth of uniform flow is the unique value of the flow depth with which a fixed discharge can pass through the channels of the first kind as uniform flow. We know that the channels of first kind are those channels for which the value of the side slope m is greater than equal to 0. So rectangular channels and trapezoidal channels fall in this category of channels of the first kind. Now the calculation of the normal depth of uniform flow is very important in context of analyzing the uniform flow. So we are going to discuss on the calculation of it for the channels of different shapes, for a few different shapes. Let's take an example of a rectangular channel. A rectangular diagram of a rectangular channel has been shown on your right. The width of the channel is b, and let's assume that the normal flow depth here is y naught. So our motivation is to calculate y naught here. So for this channel, of course, the cross sectional area of flow capital A is given by by naught, and the weighted perimeter is given by b plus 2y naught, and the hydraulic radius of the channel, we know hydraulic radius is the ratio of the cross section and the weighted perimeter, so that is given by by naught by b plus 2y naught, and this can be further simplified as y naught by 1 plus 2y naught by b. Now this figure y naught by b is actually the aspect ratio of the channel. It is the ratio of the flow depth to the width of the channel, and this aspect ratio decreases with decreasing flow depth and with increasing channel width. So for the channels for which the depth of flow is quite less as compared to its width, so for very wide channels for which the depth of flow can be is negligible, or let's say very small as compared to its huge width, so in that case this term y naught by b becomes negligible, and the hydraulic radius can be approximated as the flow depth of the channel, or r is approximately equal to y naught. These type of channels are called the wide channels, and for wide channels, of course, the hydraulic radius is approximately equal to its normal flow depth. So if we apply Manning's equation for such a channel, then we get capital Q equals to 1 by n into capital A. Capital A is the cross section of the channel, capital A into y naught to the power 2/3 and s naught to the power half. So here notice that the hydraulic radius r has been replaced by the flow depth y naught, since this is a wide channel. And if the cross section, if we substitute the value of the cross section, then we get Q equals to 1 by n into b into y naught to the power 2/3 into S naught to the power half, which is the first equation of the channel. So the discharge intensity is given by Q, small q, equals to capital Q by B. So discharge intensity is of course the total discharge by the width of the channel, which is given by small q, equals to 1 by n into y naught to the power 5 by 3 into S naught to the power half, the second equation of the channel of the slide. And the normal depth, if we manipulate the equation, then we get the normal depth is given by y naught equals to small q into n by root under S naught whole raised to the power 3 by 5. So this is the expression of the normal depth for of uniform flow in a wide rectangular channel. And it has been found that for this approximation for wide channels is acceptable for an aspect ratio y by b less than 0.02. For channels, rectangular channels with aspect ratio greater than equal to 0.02, we have to apply the conventional Manning's equation, and we can write that q into n by root under S naught equals to a into r to the power 2/3. That's of course another form of the Manning's equation. And the term a r to the power 2/3, which is a representation of the discharge capacity of the channel, or let's say the conveyance of the channel, that can be written as substituting the values of the cross section and the hydraulic radius, can be written as b y naught to the power 5 by 3 by under bracket b plus 2 y naught to the power 2 by 3, and which again can be manipulated to y naught by b to the power 5 by 3 into b to the power 8 by 3 whole divided by under bracket 1 plus 2 y naught by b to the power 2 by 3. So here if we non-dimensionalize the term on the left hand side of Manning's equation, then we can get q into n by root under S naught into b to the power 8 by 3, that equals to eta to the power 5 by 3 by under bracket 1 plus 2 eta to the power 2 by 3. So this is a non-dimensional form of the same equation. By substituting the values of values of cross section and hydraulic depth, we have obtained this equation in a non-dimensional form. And here eta is the aspect ratio y naught by b, and so this in this non-dimensional form of equation can be plotted easily as phi n. Phi is a function of eta. So this plot will easily, using the plot, we can easily derive the normal depth of a rectangular channel, which is not a wide channel. So moving on from rectangular channel to trapezoidal channels. So here we try to calculate the normal depth of uniform flow for a trapezoidal channel. A trapezoidal channel has been shown on your right. So the which has a base width of capital B, a flow depth or normal depth of y naught, and a side slope of m/1. So for such a channel, trapezoidal channel, cross section can be given as a equals to b plus my naught into y naught, and the weighted perimeter is given by capital B plus 2y naught under root m square plus 1. So the hydraulic radius, which is the ratio of the cross section to the weighted perimeter, is given by b plus my naught into y naught by b plus 2 y naught under root m square plus 1. So again we use the Manning's equation here, and using the form qn by root under s naught equals to a into r to the power 2 by 3, we can write by substituting the values of corresponding terms of a and r, we can write b plus my naught to the power 5 by 3 into y naught to the power 5 by 3 by under bracket b plus 2 y naught root under m square plus 1 whole raised to the power 2 by 3. So again we non-dimensionalize both the sides of this equation, of the equation written here, and we get that q into n by root under s naught into b to the power 8 by 3 equals to 1 plus m into eta to the power 5 by 3 into eta to the power 5 by 3 by whole divided by 1 plus 2 eta into root under m square plus 1 whole raised to the power 2 by 3. So on the right hand side of this equation, which is the last equation of the slide, can be written as a function phi of eta and m. So here notice that I mean, as compared to the rectangular channel, here one extra parameter has been introduced, so that is the side slope m here, and the non-dimensional form of this equation, which is given by qn by root under s naught into b to the power 8 by 3, which equals to phi function of eta and m. This can also be plotted, or it can be represented graphically, and using the graphical plot again, so we can easily derive the normal depth of uniform flow of a trapezoidal channel. Now a tabular solution can also be given as an aid to calculate the normal depth of such trapezoidal channel. This table is shown in the next slide. So this is an example of a table in which the function phi has been tabulated against values of eta and values of the side slope m, different values of the side slope from 0 to 2.5. M is equal to 0 here, of course, means a rectangular channel, and any value of m greater than 0 denotes a trapezoidal channel. So this is only a part of the table. This is not exhaustive. So I mean, for any a detail or other values of the value of phi against eta and m, please consult any textbook. Now, from the calculation of normal depth for a few open channel sections, let's move on to the concept of one very important thing. That is the hydraulically most efficient channel section. Let's introduce the concept first. The hydraulic radius is, of course, a ratio of the channel cross section and the perimeter or weighted perimeter of the channel, and hence the conveyance, with the concept of conveyance has been introduced before. So the conveyance, which is given by A, capital A into r to the power 2 by 3, here the value of the conveyance increases with a decreasing weighted perimeter of the channel. So given that the other parameters, the cross section is given or fixed. Remember, conveyance is a representative of the discharge capacity of the channel. So that means that for a given channel of given cross section, if we can decrease the perimeter, then the conveyance is going to increase, or the discharge capacity in turn is going to increase for the channel. So here for the given channel, for a channel for which longitudinal slope, roughness coefficient and area of cross section, those are already pre-designed. A channel with a minimum parameter will be the one with highest discharge capacity, and thus that channel section can be called as hydraulically the most efficient channel section. So this is the concept of hydraulically efficient or most efficient channel. And note one thing, that of the many shapes that's possible for an open channel, semicircular channel is an example, example of a channel for which a perimeter, weighted perimeter, becomes minimum for a given cross section. But semicircular channels are not preferred everywhere for different reasons of stability and other logistical problems are there. So normally the most of the man-made channels we encounter, those are mostly trapezoidal. Trapezoidal channel is always preferred the most, and then for a few cases rectangular channel is also constructed. Semicircular channels, man-made channels, are not well preferred many a times. So then we have to actually determine the conditions for which the channels of other shapes like rectangular or trapezoidal channels becomes hydraulically most efficient. We take an example of rectangular channel at first, and of course the area of flow is A equals to B into Y, and the weighted perimeter is given by B plus 2Y. Here B can be written as A by Y, so weighted perimeter can be written as capital P equals to A by Y plus 2Y. So for this channel, as we discussed already, mentioned that the longitudinal slope, the roughness and the cross section, those parameters are already given, already designed. So we can the only variable that we can play with is of course the flow depth here. So if we try to achieve a minimum perimeter of a channel, then if we try to achieve the minimum perimeter of the channel with respect to the flow depth, then we differentiate the perimeter with respect to y, and dp by dy here is given by equals to minus a by y squared plus 2. Note here that a, the cross section, is a constant here. So in other words, a can be given as equals to 2ye square. Here the subscript e has been used to indicate the most hydraulically efficient channel. So a equals to 2 into ye square, or ye can be written as capital BE by 2, or BE equals to 2ye. BE is the width of the channel. So note here that for a rectangular channel of given cross section, the hydraulically most efficient channel section is obtained when the depth of flow is half the channel width, or the channel width is twice the depth of flow. So that's the condition of at which the channel becomes hydraulically most efficient. The hydraulic radius can be calculated here as R equal RE, which equals to A by P, And if we substitute the terms, then we can see that the hydraulic radius equals to half of the flow depth here. So that's another result, important result here, that for the channel to become hydraulically most efficient, the hydraulic radius would be half of the flow depth. Next, we take an example of a trapezoidal channel. A trapezoidal channel has been shown on your right, and for this trapezoidal channel, note here that the area of flow is given by A equals to B plus my into y, or B can be written as A by y minus my. So the weighted perimeter P can be written as, by substituting the values, P equals to A by y minus my plus 2y into under root m square plus 1. So for this trapezoidal channel, when other parameters are fixed, of course the longitudinal slope and the roughness are given, and then the cross section is also given, and the side slope is also pre-designed, so they are fixed. So again, to obtain the hydraulically most efficient channel, we differentiate the weighted perimeter by the flow depth, that is dP by dy, which equals to minus A by y square minus m plus 2y into root under m square plus 1, which equals to 0. And if we change sides, then we get the cross section of the efficient channel, which is given by A equals to under bracket 2 into root under m square plus 1 minus m into y square. So the bottom width of the channel BE here is given by A by ye minus mye, which equals to 2 into ye under bracket root under m square plus 1 minus m, and the weighted perimeter, by substituting the values of other parameters, we get that PE equals to 2ye under bracket 2 into root under m square plus 1 minus m. So hydraulic radius here again equals to A by P, which is again becomes ye by 2. So note here that for this trapezoidal channel as well, the hydraulic radius for the most efficient trapezoidal channel is also equals to half of the flow depth. Thus we have achieved the cross section, the base width and the weighted perimeter, these parameters of hydraulically most efficient trapezoidal channel. Now let's look at the figure again. In the figure of the trapezoidal channel, you can see that OS gives the flow depth, that's ye. OT here can be written as OR into sine theta, and sine theta can be written as 1 by root under m square plus 1. So OT equals to OR by root under m square plus 1. Now OR, the half of the top, which is half of the top width of the channel, can be written as half of BE plus MYE, and substituting the value of BE from the previous slide, we have already derived an the expression for BE in the previous slide. Please look at that, and substituting the value of BE, we can write OR equals to YE into under root m square plus 1. So if we substitute the value of OR in the previous equation of OT, then we can get OT equals to, again becomes YE. So here OS equals to YE equals to OT. So we can do this calculation for the other side of the trapezium as well. But most importantly, it means that a semicircle can be inscribed inside the trapezium with a radius of YE here. So for the hydraulically most efficient trapezoidal section, a semicircle can be inscribed inside that trapezoidal section with a radius of YE. So that's a very important conclusion that we get here. And this also makes complete sense, as we mentioned before, that semicircle is one figure for which the perimeter becomes minimum for a given cross section. So we get that that result here again. Now, in the last slide, couple of slides, what we derived is that we derived a hydraulically most efficient channels, trapezoidal channel section, considering only the depth of flow. So we differentiated the depth of flow, differentiated the weighted perimeter with respect to the depth of flow, and equated that to 0 for the most efficient channel section. While doing that, you must have noticed that we kept the side slope, value of the side slope m equals m as constant. We treated m as constant. So m can also be a variable. So if we consider that m is also a variable, the side slope can also vary for a efficient channel section. Then what we can do is that we can differentiate the weighted perimeter. The weighted perimeter we are talking about now is that of what we have already achieved as the weighted perimeter of the most efficient section, considering y as variable. So we are going to differentiate PE with respect to m and equate that to 0 to obtain a hydraulically most efficient trapezoidal section with respect to m. So using the previous derivations, we can write the last equation of the slide: PE equals to 2 into under root a under bracket 2 under root m square plus 1 minus m. So this is the expression what was derived before, and if we differentiate this expression of the weighted perimeter and equate that to 0, then we get that the side slope, the value of m of the most hydraulically efficient channel section equals to 1 by root 3. Note here that m can be written as cot theta here, where theta has been pointed out in the figure on your right. That m is nothing but the value of cot theta. So if cot theta equals to 1 by root 3, then theta equals to 60 degree. So in other words, we can see that the hydraulically most efficient channel section of a trapezoidal channel, the side slope, the angle of inclination of it will be 60 degree. So what we do now is that we substitute the value of m, that is 1 by root 3, in the expressions what have been derived before, and we can get the values of the parameters like hydraulic radius, weighted perimeter, channel base width, and area cross section for the hydraulically most efficient trapezoidal section, which is given by PEM equals to 2/3 of YEM. Note here the suffix EM denotes the most efficient channel section considering both depth and side slope. So the weighted perimeter of the most efficient channel section is PEM equals to 2/3 of YEM, and capital B EM equals to 2 by root 3 YEM, and cross section of flow AEM equals to root 3 into YEM square. So those are the parameters for the hydraulically most efficient trapezoidal section for design. Looking at the figure again, let's see that the length of the inclined side of the trapezium L can be written as L equals to 2 by root 3 into Y, or LEM equals to 2 by root 3 into YEM. And this figure 2 by root 3 into YEM is equal to the base weight BEM of the hydraulically efficient channel. So in this case, this is another very interesting and very important result, that for the hydraulically most efficient trapezoidal channel section, the length of the inclined side becomes equal to the base weight of the channel. So in other words, hydraulically most efficient trapezoidal channel section is one that for which the section is 1/2 of a regular hexagon. So this is, the trapezium becomes 1/2 of a regular hexagon for which the sides are equal. So that's all for now for uniform flow, and we will continue our lecture on gradually varied flow and rapidly varied flow in the coming lectures. Thank you very much.